So I will present here my work, which is not a finished work. It's a start of something bigger that I try to build with time. Something around, as you mentioned, Nicolas, how we can enforce, well, the ability to transfer knowledge from an agent, a reinforcement learning agent, to a human. And this work here, this little piece of work is, just a little part of this. I will present to you why am I interested in this question, why it can be important overall, and how, of course, it works, and what have I built. So let me just start my timer so I don't take 40 minutes. And, and let's start. So a quick recap of reinforcement learning for those among us who have not had the good opportunity of working with reinforcement learning. Reinforcement learning is about interactions between an agent and an environment. Namely, an agent, like a robot, you can imagine a robot, it's a good example, is acting in an environment, namely, for example, life itself, or it can be a video game, it can be a financial market, it can be, well, whatever environment you can think of. And then this environment will react to the agent actions and give the opportunity of the agent to observe things about the environment itself. For example, with your eyes, you are able to observe your surroundings with visual information. Well, that's the kind of thing we try to study. How we can have those interactions in between an agent and an environment. You can see that there is this little R, and this little R is quite important because it's what's known as the objective of the agent. So those R's are rewards. They are rewards that are either given by the environment, like in this drawing, or given by the agent itself. So it's namely, it's the objective that the agent will try to optimize, but not only at the instant where it's acting, but for the future rewards. For example, if you play a game of chess, you do not want to only play an action that is very good at the time state t. You do want an action that will make you win afterwards. So long-term consequences. So yeah, the agent objective in reinforcement learning is to maximize the gain, the return, which is the sum of the future rewards. But to do that, it will change its behavior that I will not spy. Pi being a function that to a state, to an observation of the agent, will tell how the agent will act given an observation that you give to him. And the reinforcement learning is something very general. In fact, most of supervised learning and learning algorithms can be considered as only special cases of reinforcement learning, but that's for later, I guess. And you can ask yourself, well, okay, reinforcement learning is a nice framework. It's very general and very vague. So does it work? Is that useful in the real world? And if you're here, you probably know that, it is. In fact, when we have beaten the world champion of Go, not with reinforcement learning, but what's funny is that the AI that did beat the world champion was crushed afterwards. Crushed. It's the difference between this bar in green and in red is 100-0 matches. So 100 win for reinforcement learning versus 0 win for supervised learning and planning only. So that does mean that it does work, and it does work not only on the game of Go, but in fact the same algorithm, AlphaZero, was allow you to beat the best player of chess, shogi, or Go that you have in humankind. Or, for that matter, it also had the opportunity to beat any other algorithms at the time. Okay, so reinforcement learning is cool for board games. It does work for board games, but that's it. Of more complex games like Atari games were all solved that we all on all Atari games now we are able to achieve superhuman performance, and also we are able to beat StarCraft pro players at StarCraft using reinforcement learning. So yeah, reinforcement learning works. It's hard to set up, but when it works, it does work very well because this generality and this vagueness allow him to learn very complex behaviors, and unconstrained by the environment in which it is. That's what makes it powerful, because it can learn from one game to the other, unlike classic algorithms that were built to only for one specific game. And why should we be interested in explainability in reinforcement learning? Because this whole talk and my whole work is about how we can make those agents able to transfer knowledge to us. And why does it matter? Well, often we consider that we often expect AI to gently stop at human intelligence and ask us what will come. The truth is, if we do someday achieve human level intelligence, it is very probable that the AI train will not stop at the human level station. And if it does arrive, it is very strange to imagine a world where you have no idea how those algorithms are thinking, and they can't transfer knowledge to you, but they are better than you in every task. It's just like if you had someone in front of you who is a very good player, but unable to explain to you why it is better than you in any way. Imagine if you had to learn having a teacher not telling you how to do stuff better, but just telling you that what you did was not the best thing possible, and that you could have done better, which was that. And that's it, without no further explanation of how, why, and so on. Just that was not optimal. You had something that was, you had a better play to do, and that's it. So that's why explanation matters. In fact, there is a whole lot of reasons. There is a lot more reasons that explainability matters, but that's past this scope of this talk, I guess. So yeah, the big question that I'm asking myself and that started this work is, how can humans learn from those superhuman agents? Well, it starts by trying to quantify how does one transfer information to another. And for that, I studied the literature of what is done in explainability. And from my exploration, I came up with these separations between how you can explain things to one another. I've cut the ways you can. I've separated the ways you can explain from one human to another, or from one agent to another, to how you can transfer knowledge and behaviors in those categories. The first one being low-level informations, which can be translated with the question, what is important to observe to take this action? In fact, if you do work on explainability, but on other domains of AI, well, everything is always at low level, because you try to explain a single decision at a single time step, given its input. And this is explainability in deep learning. But this is not the only thing in reinforcement learning, because we do not take only one action. Actions are only part of a bigger plan, and higher levels of focusing what to transfer. For example, the level 1 action being what actions are important. Actions being the unitary decisions that you make which one of those actions were important. In a game of chess, for example, this is quite visible. If you do make a big mistake, well, the action will be very important. That's a way of thinking about it. And you also have higher level of actions, which are structure of actions. What structure of actions are important, and we will come back to that later. Maybe first let's try to make a zoom on the low level to make sure you've understood this notation. For example, to explain low level, to have a low level explanation of your agent, you can try to see what was important in the observation to take the decisions. In Pac-Man, this is something you can use techniques, explainable AI techniques, explainable deep learning techniques to be precise, to try to visualize what was important in the input. And you can see here that, well, the number of lives available was important in some way to the decision of the agent at this point, but also, of course, the position of the player and the position of the little dots near him. You can also have attention maps or other techniques, and what you can see from that is that clearly, having only low-level information is clearly not enough, because it is highly subject to interpretation. Well, if you have this importance, it doesn't tell you what's the bigger plan, what's the plan of the future actions, and so on. It tells you, okay, what was important at that time precisely, and that's why that's why in this work I focused. I try to quantify options importance. What are options? Options are a structure of actions. They are, you can think of it as a little behavior. You have the math here if you are interested, but just listen to this. Options are just skills. For example, if you go and fish something, you will use the option fishing. Why? Because it does modify your behavior. It is a behavior that is specific to the case of fishing. Well, if you are fishing, the way you will act will be very different than if you are skateboarding, for example. And fishing and skateboarding are some skill sets that are very different. That's what options are. They are structure of actions that are collapsed together because they are part of the same sub-behavior, if you can think of it like that. And so my question was, because options are not something that I've invented, my question was how to quantify that some options should be learned in priority. For example, well, in life, you have a whole lot of options to learn, but you can't learn everything. You have to start somewhere. And yeah, how to quantify that some options should be learned first if you want to achieve some goal? Well, my idea was that this importance of an option, whatever it was, should be a function of some kind of worth and some kind of commonness. Because if think about chess, for example, you could have a very good move and a very good set of moves, but if you can never use it, well, it is not that important. And on the opposite, if you have a set of moves that is not that great, but that is very, very common, well, it might be important as well. Openings, for example, in chess are very common and not that much worth it. They don't increase your chances of winning that much. But if you don't do them nicely, because they are present every game, you will be a bad player overall. And on the other way, endings in chess are quite the opposite. They are very worth it because they are the ones that makes you win, but they are not common at all. Happens nearly one time, except for a few endings that are very common. Most of the endings that you will ever do in chess are unique. So they are not that important to learn, at least not in the at first. And this worth, you can also kind of separate it between two other variables. One, which is the utility, so how much expected rewards, how much rewards you expect to get if you play this option. The complexity, so how hard it is to learn and execute that option. So if we want to quantify the option importance, in my mind, we have to compute three metrics. One, which is the utility, how much reward to expect, and it is quite easy to do so because it is very implemented already in the option framework. The commonness, how frequently it can be used, and for that, again, it is very simple to define the option framework. But then you have the complexity, how hard it is to learn an option, and that's very difficult because that's not at all defined in the option framework or in any way, and it's even hard to think about how we could define this. That's why I choose to work on this part specifically, because I had no idea how this could turn out too. So yeah, here you have the big plan of the subject, why I worked on this idea of options complexity. And yeah, let's dive into it. If you try to define complexity of a behavior in general, it does seem impossible. In fact, as a human, if you try to quantify how complex it is to, I don't know, move your finger, well, it is very hard to establish how we could compute anything because it is very subjective. But that's not it. That's why I built the option graph framework. The idea is that, okay, for some things that you cannot explain, you cannot assess their complexity. It might be too subjective. But if you do have structures in your behavior, then maybe you can have a complexity that would be defined. That's why I've worked on this hypothesis, that is, explainable options can be graphed, and because I only want to be able to quantify the complexity of explainable options, of explainable things, explainable structures. And my saying is that any option that is explainable to a human can be written as a graph in some way. And that's what we will see in this example. Let's say, for example, that you want to open a window. And as a human, how would you explain to someone how to open a window, given that, for example, you have those set of windows on the right? Think about it for a second. How would you, as a human, explain to someone how to open a window? Think about it. Well, for me, it would go something like this. First, look at if there is a handle. If there is a handle, well, have you grabbed the handle? If you have not, well, grab the handle. If you have grabbed the handle, well, is the window moving if you push, pull, or slide it in any way? If it does, well, do it. Push, pull, or slide the window to open it. If it does not, well, turn the handle because maybe the window is just locked. If there was no handle, well, try to grab the window anyway with whatever grip you can have. And, well, if you have not grabbed the window, do it. And if you have grabbed the window, pull or push or slide the window. Well, it can be a bit strange to think in that graph, but if you think about it, the way that you would have explained it in words can always be graphed in some way. Well, try it as an exercise, or if you do not succeed, well, tell me, I'm interested. And why should this structure help us for complexity? Well, if you look at the features complexity, so the features being the things that make you decide, so have you done this or whatever, the questions that we had before. The questions that you ask yourself have a complexity, and it can be very difficult to evaluate this in general, because, well, it does depend on the environment anyway. So yeah, let's set it at 1 just for the example and what's coming next. But yeah, it's very environment dependent, and so we are not very interested in that. Same goes for the actions complexity. The actions themselves, well, are part of the environment and they depend heavily on it. Yeah, so those then do not depend on the agent. But still, if we do have those complexity wherever they come from and whatever are their value, how would such a graph create a relation of complexity? And then what would be the option, the complexity of the option, given that we have the complexity of fissures and actions? Well, let's take an example and with it. Let's take the example of 3 options. Option 1 being 1 is true, then you take action 1. If fissure 1 is false, then you take action 2. Let's take the option 2, which is a bit more complex, with the same thing for fissure 2. If fissure 2 is true, then you look at fissure 3. If fissure 3 is true, then you take action 1. If it is false, and blah blah blah. You get the idea. And another option, which is way more complex, and that uses the 2 previous ones just for the example. Well, to compute the complexity, you can count the number of times each nodes appear. The people, if some of you have worked on complexity of graphs, you might notice that we do not rely on, we do not keep the of edges. And you could say that there's in the information of a fissure, because the edges themselves does depend heavily and only on the fissure that it comes from. And if you count these fissures and the number of times you've used its action, option, and fissure, then you can build histogram. For example, the first histogram is just 1, 1, 0, 1, because you use 1 time the action 1, 1 time the action 2, and 1 time the fissure 1, and so on. Same things for the option 2, but you have to enroll. You have to use option 1, and in option 1 you have this graph 2. So yeah, you just add, basically you just count everything that you see, plus you add everything that is in the previous graph. And the same thing for option 3. And option 3 is a bit bigger, but if you want to look at what is option 3 in total, it looks like this. And it is way more complex to look at than this. And that's what's interesting. Those relation of complexity, because of the fact that we reuse option 2 and option 1, and we have those substructures that we reuse, then the complexity of this seems way higher than the complexity of this. And if you had to explain to someone how to do something, how to do option 3, you would explain it like this, not like this, probably. So let's compute complexities just with the algorithms that I've developed. If you look at the complexity of option 1, it is quite straightforward. You use action 1 and action 2 only 1 time, and you use the fissure 1 only 1 time. So you are forced to learn. You have to learn anyway action 1 and action 2 and fissure 1. So the complexity would be the sum of it all. And because we've set every complexities of individual action and individual fissure conditions to 1, while it is 2 plus 1 equals 3. For the option 2, we do reuse some things. The thing that we reuse, if you look at it, is the action 1, because we use the fissure 3 1 time, the fissure 2 1 time, the fissure 1 1 time, and so on. And we use action 1 2 times. So we don't have to relearn how to execute action 1, because we already know that. So the complexity would be 7 minus 1, which is 6. And then comes the interesting part, option 3. Option 3 is a bit of a bigger compute, of course, but it is still very interesting. If you do take the sum of action and physical conditions, you land up on 21, which seems very high to understand. And in fact, if you look at this graph, a complexity of 21 is just the number of nodes that there is in this graph. And it makes sense that if every node was different, well, it would be a complexity of 21, because you would have to learn each and every one of the nodes one time anyway. But it is not, because we do reuse nodes. And because we reuse nodes and substructures, well, we can count that and remove the complexity of actions that we've reused multiple times and of options that we've reused. And I won't go too much into details. We can do that in the discussions afterwards if you want to. But the ending compute makes you fall from 21 to only 9. And that's interesting, because when you think about learning this, then this, then this, well, you do have only 9 nodes to ever learn. The other, you will reuse what you have previously learned as substructures or as structure or as an action themselves. Yeah, hopefully this was clear. This was the difficult bit, but we are coming towards the end. And so I hope this compute was well understood. If not, please keep your questions for the end, which is coming very soon anyway. And what results do we have? So I made some tests on an environment that I've developed, which is the Minecrafting environment. It is an abstraction of the Minecraft game that you might know. And the idea is that you have the Minecraft game, but without the 3D environments. You just have the crafts to do, basically. And in this environment, we can define option graphs. And that's what we have here. We have the option graph of building an enchanting table. But to build an enchanting table, I need a book, 4 obsidians, and 2 diamonds, and a crafting table. And that's why I have this option graph here. And you can see that we have a high recursivity here. That is very interesting. That's where the hierarchical part comes in the title. Same thing for the book. If you look at the book himself, well, the book, to gather the book, you have to get paper, and leather, and a crafting table. So notice that, for example, I won't have to learn twice how to do a crafting table, because if I have managed to do this option, which is the book, well, that means that I already know how to have a crafting table. And so this will not be counted. And that's what we can see in this graph, which is the comparison between the total complexity if we were not reusing any knowledge that we had previously, and the learning complexity, which is the algorithms that we've just done before. And you can see that the difference is exponential with the depth of the tree of the recurrency. And so the more deep your tree of your hierarchies, the higher your hierarchy is, the more exponential the total complexity will be, and that's not really the case for the learning complexity, which seems kind of linear. And that's very interesting, because maybe it's why we can't learn for now how to have an agent go and take a diamond in Minecraft. We are not able to do that, but still we are able to beat world champions at games of Go and chess and so on. And you can wonder what's the difference, why we can't succeed. And maybe that's why we can't succeed, because of underlying in your environment, there is a hierarchy of things to learn and to compose. And to compose knowledge is not something that a neural network can do for now. For now, it does not have those relations of recursivity. And that's why this framework could be interesting further, because it can be combined with classic machine learning, deep learning algorithms, and building those graphs based on those on those algorithms. So making an hybrid of symbolic AI and reinforcement learning could lead you to have those relations of recursivity, to have the explainability that you need for that we desperately need, and also to have more performant agents on complex environments. So yeah, just taking a step back to conclude, this is a small part of a bigger picture. But still, I had a lot of fun working with it, and I'm happy to have been able to present it to you today, and I hope you liked it. Thank you for listening. It's question time if you have some.